All right. So I'm now gonna be explaining another beautiful article from Google Research, which is backward chaining, because the original I mean, um, most articles are talk about forward chaining, but backward chaining, people notice that is more efficient. It's faster because in forward chaining you have lots of possibilities. It grows exponentially. The different choices, different paths in the graph. So so people notice that backward chaining is very fast for automated reasoning. Of course, it has been done in classical automated reasoning, but now we are rediscovering it because we notice, oh, that old idea was very interesting. We should uh, remind it and review it again. And there are other articles interesting in iClear 2023 by DeepMind. They are very interesting. So the problem of old methods is that, first I should say that remarkable progress has been made on automated reasoning with natural text by using language models such as chain of thought that I explained in the previous lecture, and selection inference, which is a similar idea. I didn't review it. These techniques search for proofs in a forward direction from axioms to the conclusion. This is the forward approach. But in the backward approach, we have the conclusion, we assume that we have the conclusion, we come back. This backward is much faster, more efficient. And it is similar to what our brain does. But the old methods of forward suffers from combinatorial explosion of search space, thus high failure rates of problems requiring longer chain of reasoning, waste of time. So a machine is just trying different searches, so it's not quick, it's not fast. So we rediscover classical automated reasoning by backward chaining, which is called the Lambda algorithm. So it decomposes reasoning into 4 submodules, and these submodules are simply implemented by a few short prompted language models that we know very well. So what are these modules? First of all, what is the final goal in AI? It's logical reasoning, and of course reasoning. In my playlist, when I say reasoning, I mean that common sense reasoning, logical reasoning, even critical thinking, which is a system of basic subsystems. And there are many ways that you can do, and all of these reasoning is the third faculty of Immanuel Kant in philosophy. But nowadays we don't need philosophy because we have already implemented them on our machines. And one day the human, the machine may be very jealous of the creativity of the human, and that's why AI safety is important. So we go from our conclusion, for example, our goal is Eric is nice, and we have a set of rules. These rules could be just fancy or just fantasy. It could be magical. It could be realistic. It could be in legal domain. For example, in argument mining, you have something. So it depends on what you are doing in your company. You have some rules, and there are some facts as well. So facts are different from rules, although they may seem related, but they are different. So for example, when we say Eric is nice, you are using rule number 6, because an individual who is big, red, and young is also nice. So we understand that we should check all of them to make sure that Eric is nice. Eric is big, Eric is red, Eric is young. We know that Eric is big because it's a fact check. Eric is big. We use the facts. And also, so you have different set of modules. Some of them are rule selection, some of them are decompose, some of them are fact check, and some of them are assignments. So there are two major approaches to logical reasoning. As I said, forget forward chaining. It's too complex, it's too slow. We don't do it in our human brain. Human brain does not do that. So it requires a combinatorial search, exponential size, so we skip it. But backward chaining, which is the idea of this paper in Google Research, uses the old idea of classical logical reasoning. And it decomposes into sub-goals until the sub-goals can be proved or disproved based on the theory. So the Lambda algorithm is that we focus on performing automated reasoning over facts, natural language assertions such as nice people are red, that are coherent but not necessarily grounded in reality. A rule is a natural language statement that is either of the form or can be rewritten in the form if P then Q. This is a rule. So P is the antecedent, this is antecedent, and Q is the consequent of this rule. And we have several rules, and so this is the backward chaining that I explained in this figure. So to enable applying a backward chain for text-based reasoning, we introduce 4 language model-based modules. As I said, the first module is fact check, the second module is rule selection, the third module is goal decomposition, and finally the sign agreement is the fourth module. So we go through each of them. We implement fact check with 2 submodules. The first submodule selects the facts from the set of facts that is most relevant to the goal, and the second submodule verifies it. So select, then verify. You will see in the appendix how these algorithms are implemented using our few-shot learning. And in rule selection, in module 2, as we did for fact check, we implement rule selection with 2 submodules. The first submodule identifies the consequent of each rule, and the second submodule takes the rule's subsequent consequence and the goal as input and identifies which one unifies with the goal. And goal decomposition, the goal decomposition identifies the sub-goals. And the sub-goals are identified based on the antecedent of R. And finally, sign agreement. In the case where we succeed in proving the antecedent of R, of rule R, whether the goal is proved or disproved depends on whether the sign of the goal agrees or disagrees with the sign of the consequent of R. For instance, for the goal Eric is nice, since the sign of the goal agrees with the sign of the subsequent of rule 6, and the antecedent of the rule is proved, we conclude that the goal is proved. However, rule 6 is not going to be a nice individual, then the sign of the goal would disagree with the sign, so we would conclude that the goal is disproved. This motivates the fourth module, the sign agreement. which I described here. So algorithm 1 provides a high-level description of how four language models described earlier can be integrated with the backward chain to enable text-based logical reasoning. So initially, the algorithm uses fact-check module to check if G can be proved or disproved using the facts. If G cannot be proved or disproved, then the algorithm checks the depth. If depth is 0, then the algorithm stops and returns a no, indicating that G could not be proved or disproved. The rule selection module is used to identify the rules from R whose consequent unifies with G. Once the set is identified, if Lambda can start with the rules that have higher chance of successing at disproving the goal, it can save computation and less error prone. And this is important caching and avoiding loops because Lambda is a recursive algorithm during the proof. So algorithm 1 may be called with the same goal multiple times. For instance, consider the goal Eric is nice for the theory in figure 1. Applying rule 6 breaks the goal into 3 sub-goals. The first one is Eric is big, which is proved using fact check. For the second sub-goal, rule is used to compose it into 3 sub-goals, the first of which have proved before. Since we have already proved this sub-goal, we can save a fact check. So it's like dynamic programming because you don't want to do brute force, search everything. You want to take advantage of some structure. And so this is another example. Dave is not green. Fact check it. Use rule 6 in this direction or rule 3 in this direction. Use the module decompose. Also rule selection. Again decompose. Again fact check, rule check. And finally assign it is correct assignment. So the pseudocode for the fact check, because first you should select and then you should verify it. So fact 1, then fact 2, and so the most relevant fact is fact 1. This is how you implement it. So for verifying if the goal can be derived from the selected fact, we use the following prompt. For example, in the prompt we say question and inference is the fact x1 d, and so it is just a substitution. And for rule selection is again the same. We say we know rule 1, we know rule 2. Their inference says rule 1 implies x1 and rule n implies xn. For example, k, rule 1, rule 2, rule m, and so on.